Good afternoon. We're starting part 8. Part 8 is on linear momentum and essentially what that is and everything that relates to that. And so what is linear momentum? Well, it's a vector. We're back in vectors. All that was energy. You'll notice that everything in energy and work and power, everything that was involved, besides the force and the displacement for the work, but everything else, all of the resulting quantities were scalars. We didn't have to worry about directions at all. That was the powerful stuff with it. Very, very nice stuff because it made it easy. Now we're back with vectors. Because of course we are. Why wouldn't we? The linear momentum is also called the quantity of motion of an object. It is a physical quantity that, again, humans invented, much like energy, and that we determined was going to be conserved. It was going to be conserved during a collision. Energy was going to be conserved when one object was in motion. Here it is when one object undergoes a collision. Something that makes it change direction dramatically in a very, very short amount of time. First bit is to determine how we write it mathematically. It's very well to say it's the quantity of motion, but what is that? The linear momentum P is equal to the mass times the velocity of the object. You'll notice that it is a vector quantity. It has direction as well as magnitude, and its units are, well, the product of the units of the mass and the velocity, therefore kilograms meters per second. Note the small dot here, very small. It's not a dot product, that would be a bigger dot, but it's here to symbolize that we're multiplying the two units together and not just bringing a bunch of letters together. Because it's a vector equation, we'll almost always, if not exactly always, split it into its components. Where we have here the linear momentum in x is equal to the mass times the component of the velocity in x, same in y, same in z. Like most things, most objects, if not everything in the universe, goes in 3 dimensions. So we have 3 components to the velocity, 3 components to the linear momentum. In most of our cases, however, and at this level in mechanics, we can ignore the z dimension, much like we did with forces. We'll arrange our perspective so that everything happens in a plane, either vertical or horizontal. The lab activity 10 or 11, one of those two was on linear momentum, was all exploring this. It was a collision of 2 pucks. I'll make the files open so you can look them up and see, if you want to, what is going on in there. For our purposes, the z dimensions, we don't really care. So now that we've written down what the linear momentum is, we can rewrite Newton's second law, the real Newton's second law, the way Newton himself, formulated it, said it. The original statement of Newton's second law is this. It is, the rate of change of the momentum of an object is directly proportional to the net force applied, and this change takes place in the direction of this net force. We had the sum of the forces is equal to the mass times the acceleration. Knowing now that what the linear momentum is, we can rewrite this and write sum of the forces is equal to dp dt, or the net force is the change in momentum, the rate of change in momentum. If you want to make sure that you can go from this one to that one, just take the derivative of the momentum, knowing that the mass is kept constant. Use your rules of derivatives and you'll go back to this. So that's the basics of linear momentum. With these 2 definitions, we can move on to the next stuff and steps. I'll see you then.